on page 41 in your practice book, this is a review of scientific notation from lesson 4. You should have read over the examples because question number 1 had its answer written for you in the example. Number 1 says, in the example problem, there's your hint, this number is this in scientific notation. What is the standard form of 10 to the 9th? It was right here. 0.0000000001. Because 10 to the negative 9 has to be less than 1, and it was 9 decimal places away. Number 2, write a number that is greater than 1 in scientific notation and explain how you know it is greater. Any number in scientific notation that has a positive exponent will be greater than 1. So I could do 5.3 times 10 to the 2 if I wanted to.
Could that be the same as 1?
No, it said greater than 1. The exponent has to be positive, and that tells us that our number is greater than 1. Number 3 says explain why you might want to write very large and very small numbers like the ones in the example in scientific notation. The main reason is because those zeros get messy. Okay, they're hard to work with. It's hard to work with lots of zeros. Make those numbers smaller and easier to work with by using scientific notation. Now, they was not asking you to calculate anything. They just wanted to know, why might you need to use scientific notation? On the back, number 4. Write these numbers in scientific notation. The first thing you should notice is that both of these numbers are less than 1, which will tell you that your exponent has to be negative. We have a decimal here. I need to move it so that my number is between 1 and 9. I'm going to make it 6.08 times 10 to the, it has to be a negative exponent. Now I'm going to count how many place values I need to move this. 1, 2, 3, 4, 5, 6, 7. So the first one is negative 7. The second one, I need to move my decimal between the 9 and the 2 so that my constant becomes 9.2 times 10, and I'm going to count my decimal places, 1, 2, 3, 4, 5, 6, 7, 8, and it is negative because the number was less than 1. Number 5, write 2.06 times 10 to the 10th in standard form. You should notice the positive exponent. That positive 10 exponent says that in standard form, 2.06 is 10 place values bigger than it currently is. So 206, that's 2 decimal places. I've got to move it 8 more. 1, 2, 3, 4, 5, 6, 7, 8. Giving me this answer. Number 6. Use the table to answer the questions. Write each population in scientific notation. Now, all of these numbers are greater than 1, so our exponent will be positive. Positive exponents on these. I'm going to move my decimal between the 1 and the 3, so 1.39 times 10, positive exponent of 369. Germany, I'm going to move my decimal so that my constant becomes 8.27. My exponent will be positive. I just need to count 1, 2, 3, 4, 5, 6, 7 decimal places. And then Martinique, I'm going to change the constant to 4.05. And I'm going to move my decimal 1, 2, 3, 4, 5 spaces. The population of Germany is about how many times the population of Martinique. So we want Germany divided by Martinique. Germany was 8.27 times 10 to the 7th. Martinique was 4.05 times 10 to the 5th. Now I'm going to divide my constants, 8.27 divided by 4.05 is 2.04, and then it's this big long irrational number. I'm going to round it. These have 2 decimal places, so I'm going to round my answer to 2 decimal places. Here's my answer. I'm going to round that to 2.04. Now my base 10s, I'm going to use the quotient rule. 7 minus 5 gives me 10 to the 2. Now that number is in scientific notation. It doesn't tell me how many times. If I put it in standard form, it becomes 204 times. So Germany is 204 times the population of Martinique. Now if you was looking at number 7, you may have struggled a little bit because it's set up a little bit differently. A scientist uses 2.8 times 10 to the 12 cells in one experiment, which is 2,000 times the number of cells she used in a second experiment. Write the number of cells the scientist used in her second experiment in scientific notation and explain your answer. Now, think about how we've done all of these how many times greater. So how many times greater is equal to the larger number, which was the first experiment, divided by the smaller number, which was the second experiment. So now we just have to substitute it in. The number of times greater they gave us, 2,000 times greater, is equal to the first experiment, 2.8 times 10 to the 12, divided by the second experiment, which we don't know. So we're going to call it x. Now I'm just going to solve for x. I need to move the x out of that denominator, so I'm going to multiply both sides by x, which is going to give me 2,000x equals 2.8 times 10 to the 12. Now I'm solving for x. Now I'm going to divide by 2,000, bless you, which is going to leave me with x equals, I can't divide a scientific notation by a standard form, so I'm going to change my standard form from 2,000 to 2.0 times 10 to the third. Okay, that's 2.0 times 10 to the third. In case you can't read that, I wrote it to the side. Now when I divide, I'm going to divide 2.8 divided by 2.0, which gives me 1.4. Now I'll divide my base 10s using the quotient rule, and I'll subtract the 3 from the 12 to give me 10 to the 9. Now they wanted the answer in scientific notation, and that is our answer. So in her second experiment, she used 1.4 times 10 to the 9th cells. And that is all.